Glad you could join me in this very cold room. So I'll be talking about refinement, and I should say this is joint work between João, Peter, and myself at ETH Zurich. So let me quickly set the scene for what I mean by distributed programs. So imagine you are writing a server application in your favorite language, which is Rust, and you want to verify that it behaves according to some protocol. So for this simple example, we can say, okay, when this server receives a ping message, it should respond with a pong message with the same value. And that's fine for this kind of tiny example, but it doesn't really scale. So our main case study for this work was a system called Memcached, which is an in-memory cache system that clients can connect to and use as a cache. So it has an implementation in C++, but crucially it has a extensive documentation which basically specifies what is the protocol that Memcached implements. And we have developed multiple versions of sort of a subset of Memcached in Rust, starting from a very simple implementation that was single-threaded all the way to a more complex multi-threaded implementation with fine-grained locking. And essentially our research question was, is it possible to develop a methodology that can apply to such realistic protocols, can support real-world languages such as Rust, allows for the code base to evolve over time and change, by which we mean we don't want to have too tight of a coupling between the implementation and the model, allows for the eventual implementation to actually be efficient, so use things like atomics and multiple threads and so on, and all the while avoiding large manual proofs in thousands of lines of interactive theorem prover scripts. So we answered this question in the positive, I guess, with our methodology. So our methodology is using a refinement technique. So this essentially means that we want to relate the steps of the concrete execution to the steps of the model. So the concrete steps have some concrete states consisting of the program variables, the call stacks, the threads, and so on, and evolve according to, well, the definition of the Rust language, so the operational semantics. And if this is a distributed system or a multi-threaded program, then what you actually have is multiple nodes where no single node has a sort of a complete picture of the full state, and the steps that these nodes are taking aren't well ordered with respect to each other. They happen in parallel. And on the model side, well, I said we start with this specification of Memcached written in technical prose, but this is not a formal approach, so what we use is a transition system. So you can think of formalisms like TLE plus or veil as ways to do this, but essentially you need to have a notion of state of a bunch of variables and their types, and a set of labeled actions which decide how one state can move into another. And the refinement proof is essentially trying to establish a connection between all of the actions of the implementation and this model, specifically by classifying each step of the implementation into stutter steps, which don't really reflect in the model because they're sort of local changes that are not observable, and actions, which, for example, things like sending a packet to the network, which are observable to other nodes in the system. So they had better behave according to the protocol. So let's zoom in on how we verify a single step of the implementation when it's performing an action. To do this, we make the observation that most of what the implementation does is not relevant to the refinement proof, because most of what the implementation does is changes to the local state or bookkeeping or method calls, which just aren't observable by other methods. By other nodes. And so the places where the action is actually taking place, where something is happening as far as the model is concerned, we delineate using what we call transition blocks. So you can think of these as critical sections of a global lock protecting the model state. And they basically tell us a couple of important things. They tell us where is the transition actually happening. So this is where we do our refinement proof. They tell us what actions we're taking in the transition block. They tell us how the implementation is updating the environment by using standard library or IO method calls, and potentially also how the model state is updated for the sake of the proof. And so it's important to note that these IO operations, like sending packets to the network, are just not allowed outside of transition blocks. But we face some issues, I guess, because we said at the very beginning to try to develop an automatable methodology. And so we want to verify these transition blocks in a modular fashion if possible. It should be possible to verify each of these in isolation without having complete knowledge of the global trace of steps that happened before the transition block. Which means that to be a completely modular approach, we must assume that the initial model state at the beginning of the transition block is essentially arbitrary, which is an issue because we sometimes want to perform actions which have preconditions. So we need to know something about the model state at the beginning of the transition block for us to actually take an action. And so the way we solve this issue is with something we call local reasoning or locally inductive invariants. So let me motivate this with a very simple example. So imagine you have a shared counter which starts at 0, and it can be reset back to 0 or incremented by 1. And you have multiple nodes operating on this shared counter in parallel. And now the question is, if one node performs an action like increment, can it assert that the counter is greater or equal to 1 immediately after? And the answer is unfortunately no, because immediately after the increment, the other node could have reset the counter back to 0. So what we can do is say that certain actions of the system are only possible to perform by certain nodes in the system. So we give them roles or guards. So if, in this case, the reset action was only performable by the left node, then after incrementing the counter, it can actually assert that the counter is greater or equal to 1, because the other node cannot reset it. It doesn't have the permission to perform the reset action. It can only increment the counter further. And so this kind of assertion is what we call a locally inductive invariant. It is not an invariant of the system in general, but it is an inductive invariant as long as you hold on to some guards which prove that it must hold. So back to our example, we make use of guards and guarded transition systems, as we've seen, to deal with these situations. So our notion of a model is no longer just a transition system. It is a guarded transition system with a set of guards and a specification which says which guards are required for which actions. But dually, the guards are also resources in the implementation. We represent these guards as a type, an opaque type in Rust. And what is very nice is that we can rely on the existing Rust ownership type system to actually track uniqueness of guards as they flow around the implementation. And so with the guard in hand, the implementation can basically use it as a justification for a locally inductive invariant. The actual reasoning that happens at the point where we are applying a locally inductive invariant is essentially a kind of induction principle. The relevant proof rule is here on the slides, but essentially it just encodes the intuition that we have seen before. But of course, feel free to check out the paper for more details. These locally inductive invariants are crucial to our methodology, and we have seen that they can indeed decouple implementations from the model. So at the beginning, I have said we have developed different versions of Memcached, from single-threaded to multi-threaded with fine-grained locking. And as you can see in the evaluation here, although the code has actually changed significantly, so this is the first first column of numbers, the model is almost the same. Like, we have declared more guards, but it's the same model that we're refining against. So this gives us very strong assurance that these locally inductive invariants is what we want here. On the topic of the evaluation, we have also implemented algorithms from the literature, such as Paxos, or concurrent data structures like a lock-free data set, hash set, and a queue which uses different kinds of atomics for synchronization purposes. All of what I've been describing exists as a library in Rust, and more specifically in Prusty. So if you look at our artifact, you can find extensive documentation on how these types actually work, and they map quite nicely also to Rust. For example, different models in our methodology are just different implementations of the model trait. So what I haven't talked about in this talk is, well, why this locally inductive invariant reasoning is sound. So we present a small formalization argument in our paper. We need to ensure that these transition blocks are actually kind of atomic, so we use a linearization argument for these purposes. We have also specified some parts of the Rust standard library, and we talk about how to write these specifications compositionally. So to summarize, I have presented a novel refinement methodology for languages like Rust, usable with verifiers like Prusty, but really what is needed is kind of separation logic reasoning with a focus on modularity and compositionality. Our key ingredient was this locally inductive invariant concept, and all of this exists as a Prusty library evaluated on several case studies. Thank you.
We have a couple of minutes for questions. Please come to the microphones if you have questions. I might get started. What kinds of properties might you extend this to be able to verify in the future? Is there anything that's out of scope at the moment but would be your future work?
Thank you. Yeah, so for now, this focused on safety properties. So basically showing that the protocol is not violated at any step. But we do want to extend this to liveness properties as well, and we have some prior work already on this that we will publish in the future, I guess.
Hi.
Yep.
To verify your examples, do you have to manually add those guards in your code, in your implementation?
Yes, you have to add some annotations to the implementation. You need to, this is the sort of setting of modular verification, so you need to add things like preconditions, postconditions, and loop invariants, and this is where you would interact with the guards the most.
So those annotations are actually checked by Rust type system. It is kind of...
The ownership of the guards is checked by the type system, but the way you use the guards is checked by the verifier.
Oh, okay, yeah, thank you.
So that you don't create two guards that are kind of allowing you to do the same thing, or how do you manage that?
There's a set of guards that exist in the system to begin with, the full universe of guards, and you can sort of from the start give those guards away. And in the case of something like a distributed system, you have to model this initialization because it doesn't actually happen in a single program.
Okay, I was also wondering about that. Thanks.
Thank you.